material that we are discussing right now begins Chapter 5 on nuclear chemistry. And nuclear chemistry involves a discussion of nuclear reactions, nuclear changes that are different in their very essence from what we discuss with chemical changes, in that in nuclear reactions, we actually see atoms undergoing a change in their very identity, meaning the composition of their nucleus, converting into different elements as a result of nuclear changes. This is all incorporated into the topic of nuclear chemistry. Chemical reactions, on the other hand, do not involve changes in the nucleus, and atoms retain their identity, their atomic number, throughout any sorts of chemical changes. So I just want to establish here quickly that the information that we're talking about here in Chapter 5 on nuclear chemistry and nuclear reactions is fundamentally different than what we will be discussing throughout the rest of this semester, which is largely focused on chemical changes, chemical reactions that do not involve changes in the identity or nucleus of atoms. In order to understand nuclear changes, nuclear reactions, we first need to introduce the topic of radioactivity. And this information is found in section 5.1. So, radioactivity is found amongst the various isotopes of elements that we've looked at on the periodic table. So, atoms of many elements have one or more isotopes that are radioactive. And if it's a radioactive isotope, it's referred to as a radioisotope. A radioisotope has an unstable nucleus. The unstable nucleus will spontaneously rearrange, emitting radiation. And the radiation may take the form of either small particles or just pure energy. Table 5.2, page 147. And I strongly urge you, if you have your book close by, to put this video on pause and go get your textbook and turn to page 147 and look at table 5.2, which summarizes the various types of radiation that can be emitted in a nuclear change, a nuclear reaction. So notice those types of radiation take the form of either small particles, alpha particles, beta particles, positron, proton, neutron, or it may be gamma rays, the high end of the electromagnetic radiation spectrum, pure energy. In other words, you're responsible for knowing these types of radiation that can be emitted and the symbols that are used to describe them. So let's just briefly go through them. Alpha particles. Remember, we introduced the idea of alpha particles when we discussed Rutherford's gold foil experiment. He shot or projected alpha particles at gold foil to see what would happen. He knew that alpha particles were positively charged and very massive. That is because an alpha particle actually consists of a helium nucleus that's been stripped of its electrons. Its 2 electrons have been ionized, leaving just a helium nucleus with a +2 charge. Now you remember the convention that we used for discussing various isotopes. Number in the upper left-hand corner is the mass number. Number in the lower left-hand corner is the atomic number. So if you have a periodic table close by, you can see that the atomic number of helium is 2. It has 2 protons. And the most abundant isotope of helium is helium-4, for a total of 2 protons and 2 neutrons. So you can symbolize an alpha particle by just using the helium symbol with the mass number and atomic number of 4, 2, or you can go to the Greek alphabet and use the first letter of the Greek alphabet, which is the letter alpha, and use the same mass number, atomic number notation. Right, so these 2 forms are equally valid as symbols for alpha particles. Mass number of 4 and charge is +2 because it's the nucleus only of a helium atom, missing the 2 electrons, so a +2 cation. Let's move to the next particle, which can be emitted as a form of radiation, and they are called beta particles. And you can see immediately from the notation, wow, it looks like a beta particle is an electron. And that's exactly what it is. We see the symbol for the electron used. It has a mass number of 0 because it's neither a proton or a neutron. It has an atomic number of -1 because it is equal but opposite in charge to a proton. So hence the -1 charge for an electron. Another way that you can symbolize a beta particle is to use the Greek letter beta, right? Symbolized with a B with a kind of a long tail. And again, mass number of 0, atomic number of -1. The next particle that I'd like to mention is one that you probably are not familiar with. It's called a positron. And a positron is an electron-like particle, so very tiny in mass compared to a proton or neutron, like an electron is. It's an electron-like particle, but it has a positive charge to it, hence positron. So you see the symbol for the electron, mass number of 0, but the charge is +1 because positrons have a positive charge opposite in sign to that of an electron with a +1 charge. You can symbolize a positron using the letter B for beta and the mass number 0, atomic number +1, and then indicate the positive charge. This can also be left off, and it's still understood because of that +1 charge to be a positron. The next type of radioactive particle that I'd like to mention is the proton. And the proton is essentially a hydrogen nucleus. If you think about it, looking at the periodic table, hydrogen atoms have just 1 proton in their nucleus. So a proton, a hydrogen atom, I should specifically say nucleus with just a proton there. No neutrons present. The most common form of hydrogen, most common isotope of hydrogen is protium. It has no neutrons, just 1 proton, so mass number is 1 as well. So you can symbolize a proton using the symbol for hydrogen or just use the lowercase p for proton. Mass number of 1, atomic number of 1. So you see that information summarized where it says mass number and charge. Obviously protons +1 charge. Neutrons, you know, have neutral charge. Mass number is 1 because it's simply 1 neutron, no charge, so atomic number would be 0. And then the last category, gamma rays or gamma radiation, pure energy, not particle-like at all, therefore mass number is 0, atomic number is 0, and we're using the Greek letter for gamma. So these symbols you are responsible for knowing and writing in nuclear reactions and the equations for them that we'll be discussing shortly. You also see on page 147 a discussion of the biological effects of radiation. Most of us are aware before we even take any chemistry classes that exposure to radiation is not good for us biologically. And what is exactly happening when we get exposed to radiation? What are the biological effects on our body? Radiation can knock electrons off of biological molecules. In other words, we looked at ionization energy, the amount of energy needed to remove an electron from an atom and convert it into an ion. Well, radiation can supply that amount of energy. So radiation can knock electrons off of biological molecules or water in the body, forming unstable molecules. Actually, I should use the word ions. They're now charged because they've lost electrons. So forming unstable ions. For example, here's water, which is a neutral molecule, but you knock an electron off of it, and now it's going to be a +1 ion. Or the radiation, if it encounters any biomolecule, can knock an electron off of it and convert it into a positive cation. Therefore, this radiation is called ionizing radiation because it ionizes, causes charges to form on biological molecules or water. So, ionizing radiation, what sequence of events does it set in play? It forms unstable ions that we looked at right up above that are not supposed to have positive charge. Once these unstable ions form, they're highly reactive and they cause undesirable chemical reactions to take place within the cell. These undesirable chemical reactions can disrupt normal cellular processes, damages the cells, specifically can damage DNA. And as a result of the DNA of cells being damaged, cells can lose their ability to produce needed materials, for example, functional proteins. Or the cell can possibly convert and become uncontrolled in its cell growth, leading to cancer or tumor formation. Notice the effects of ionizing radiation are most pronounced on rapidly dividing cells, such as hair, skin, the lining of the intestine, and of course, children are rapidly growing, undergoing rapid cell division, so ionizing radiation can have pronounced effects on growing children. Possible long-term effects of ionizing radiation. Some of this you're already familiar with. Cancer, malignant tumors, leukemia, a blood cancer, anemia, genetic diseases, or birth defects. If the ionizing radiation hits gametes, such as eggs or sperm, it can result in children being born with birth defects. If you turn in your text to page 148, you will see there's a discussion of how you can protect yourself, shield yourself from possible exposure to ionizing radiation. And there is a table on page 148, table 3.1, that is, let's make sure I've got that right. I think I don't have that number right. It's table 5.3. So let me write that correctly here. Table 5.3, page 148. That summarizes proper shielding required to prevent exposure to ionizing radiation. And this PPE, we hear a lot about PPE as a result of COVID and preventing exposure to the COVID virus. PE stands for personal protective equipment. So what sort of personal protection would be needed to prevent exposure to, say, alpha particle radiation? This first number tells you how far alpha particles can travel just free in the air. Because alpha particles are so heavy, they can't travel very far through the air, only 2 to 4 centimeters. They are so heavy that they are massive that they do not penetrate very deeply into tissue, only about 0.05 millimeters deep. So they have a difficult time penetrating deeply into biological tissue. In order to protect yourself from alpha particles, it's actually fairly easy to do that. They can be stopped by paper or by just regular clothing. Prevents alpha particles from being able to penetrate. However, a note here, if alpha particles are ingested, you somehow imbibe or ingest some sort of substance that emits alpha particle radiation. It's now happening internally. It can be quite destructive inside of you, like a bull in a china cupboard. If somehow you ingest material, radioactive isotope that emits alpha particles. So you want to make sure you protect yourself from any sort of internal ingestion of anything that could produce that. The second type of radiation that we commonly experience or encounter in nuclear reactions is beta particle radiation. These, of course, are electrons. Notice they travel much further through the air because they're smaller particles, 200 to 300 centimeter distance in the air. Because they're smaller particles, they can penetrate 4 to 5 millimeters deep into tissue. So they have a greater penetrating ability and can cause more damage than alpha particles because they penetrate into tissue more deeply. What sort of personal protection equipment would you need to prevent exposure from beta particles coming from the external environment? Heavy cloth, like this lab coat for instance. So heavy clothes, lab coat, and gloves would be necessary to prevent exposure from beta particle radiation. The last type of common radiation that we encounter in nuclear changes is gamma radiation. So although there are other types of radiation that we discussed here, the most common that we experience from radioisotopes is alpha particle radiation, beta particle radiation, and gamma radiation. Remember, gamma radiation is pure energy, not particle-like. So not surprising, it travels much further in air than either particle-like alpha particles or beta particles. Can travel 500 meters in air, penetrates tissues 50 centimeters or more deep, meaning the gamma radiation just passes right through the organism. What would be necessary to stop gamma radiation, which is the most penetrating of the three types we've looked at? Well, you would need to have lead, for example, a lead apron that you may have experienced placed over you for an x-ray. Lead or thick concrete would be necessary to prevent exposure to gamma radiation. One last thing I'd like to mention here in this introduction to natural radioactivity is found on page 158. And if you turn in your textbooks to page 158, it discusses on the left margin, table 5.5, radiation exposure. In other words, what sources of radiation expose you to some sort of radiation listed above. So what are the sources of radiation exposure? Where are they coming from? You see the table is grouped by natural sources or medical sources or other sources. So natural sources include just the ground. There are rocks and minerals in the ground that contain radioisotopes that emit radiation. Air, water, the food that we eat all has small amounts of radioisotopes that emit radiation. Cosmic rays coming from outer space. Other types of materials, concrete for instance, all of these contain small amounts of radioisotopes that emit radiation. Medical sources are another source of radiation exposure to the average human. Dental x-rays, chest x-rays, mammogram, hip x-ray, other types of imaging will present a source of radiation exposure to individuals. And then lastly, there's other miscellaneous sources such as air travel, TVs, electronics, and radon gas. And I mentioned that because depending on what the geographic location is, some sorts of rocks or types of rocks and soil are more likely to emit radon gas than other types. And you see page 151 of the text has a nice discussion of radon gas exposure and how that can vary, causes of it, and how it can vary geographically. You also see on page 158, table 5.6, discussing lethal doses of radiation and that's symbolized by capital L, capital D, with a subscript 50. And that stands for lethal dose, whole body radiation exposure that is expected to cause fatalities in 50% of the population that receives this whole body radiation exposure. So that's what we're talking about when we talk about lethal dose of radiation, the amount of whole body radiation expected to cause fatality for 50% of the population. And you see that page 158, table 5.6, gives you LD50 values for various life forms. Humans are listed, and you see the number 8 sieverts as the LD50 dose, and sieverts is a metric unit expressing the biological effects of radiation. You're not responsible for knowing the definition of a sievert. You can look it up, it's in the text, but I'm not requiring that for this class and for the scope of our purposes here. But the numerical comparison is interesting. LD50 doses of radiation for humans are 8 sieverts. That's the amount of whole body radiation predicted to cause fatality in 50% of the human population receiving this dose. For bacteria, notice bacteria from a radiation standpoint significantly hardier than humans. LD50 doses for bacteria would be up at 500 sieverts. And this is interesting to me. Insects trump bacteria. LD50 doses for insects are 1,000 sieverts, right? Many times more than either humans or bacteria. And what is it that insects have that we don't have, or bacteria? And the answer is insects have an exoskeleton. Their skeleton is on the outside, and that serves as some protection to them from the damaging biological effects of ionizing radiation. So I like to comment here that there's this kind of dark humor that in the event of a nuclear war, all-out global nuclear war, the only organisms that would survive would be cockroaches. And this information here does lend credence to that dark joke. But hopefully we humans will figure out how to avoid that, not only now, but in the future, indefinitely, perpetually ahead.